Hi Year 12s, this is Mr. Lim, and this is the last video on the Year 4 Redox. It's the WACE exam questions. Let's have a look. Right, so again, you have videos that you could watch if you don't understand this question, the average score for this by all of the kids for that year, and then any notes from the examiners if they had any for these questions. All right, so let's have a look. The corrosion of brass plumbing fixtures has been identified as a possible cause of presence of lead in drinking water. Brass is an alloy of copper and zinc, but it contains lead as well for improved machinability, which just means it's easier to make into whatever shape you want. The corrosion of brass is a redox process, so with an electrochemical cell forming on the surface of the brass as illustrated below. So this is exactly the same as the corrosion stuff that we've done in the video, but instead of it being with iron, it's with these other metals, and that's totally possible because corrosion can be with any metal. So which of the following identifies the anodic region and the cathodic region in the direction of electron flow? Okay, so let's have a think. Anode is where oxidation occurs always, and cathode is where reduction occurs. So which one is having oxidation occur? That's this one here. Okay, where the metal is turning into metal ion, and then the reduction is happening over here. So anode is that one there, so we can get rid of that one there and that one there. All right, then we just have to think, is it going from the anode to the cathode or the cathode to the anode? So let's have a think. Anode is loss of electrons. Okay, so anode is oxidation, which is loss of electrons, so it's actually going this way. So it's going from that funny little trident to the little star, which means it's A and not B, and not C, sorry. All right, that's how you work it out. Okay, same question. The overall equation for the reaction of lead with oxygen is as follows. That one there. What is the theoretical E value for this PbO2 under standard conditions? So what you're going to do is find these two reactions. Now, the problem is that you've got to make sure that you're finding the right ones because there's quite a few different reactions. So this one, Pb to Pb here, you should be able to work out that this is Pb2 plus because that's OH minus and there's two of them. Okay, so this is Pb to Pb2 plus. Okay, which is at negative 0.13 volts. Okay, and then the other one is the O2 going to the OH. So you're going to find that one, and there's quite a few of them. It's at positive 0.4. Okay, so at positive 0.4 volts. Okay, and that's the O2 to plus H2O goes to 4OH to there, 4OH minus. Okay, so you've got to make sure that you look for the right one because the oxygen is shown in a number of different places, and don't just go for the first oxygen that you see. You make sure you find the one with the right reactants and the right products. Okay, so that one's there, so therefore you can work out that the difference between these two values is what, 0.53. Okay, so 0.53, and there you go, 0.53 volts. Ta-da! Right, next. The composition of brass can be adjusted by adding various metals. Which of the following metals would not undergo corrosion if added to the brass? Okay, so if you're thinking about which would not undergo corrosion, why? For what reason? Why would this metal not undergo corrosion? Because the other metals are acting as sacrificial anodes for it. So that means that this has to be less reactive than the other metals, which means it needs to be higher on the standard reduction potential table. Okay, so if you're looking for the one that's higher above all of the others, it's going to be silver. Okay, you can find all the others. Silver is the highest one on the standard reduction potential table, and therefore will not undergo oxidation before all of the others. All right. Next. Okay, which statement is correct? Only 51% of this people got this one. It's because they probably didn't read the question. Okay, fluorine oxidize, chlorine oxidize. These cannot occur because you cannot oxidize fluorine and chlorine. You can reduce them, but you cannot oxidize them. Right. So read the question. Yeah. So chlorine can be reduced by potassium bromide. So you find chlorine, where is it? It's at plus 1.36, and you find bromide, and that's at plus 1.08. So that is true, but not by potassium iodide. Potassium iodide is even lower than the bromide. So therefore that is also true, So therefore that is the correct answer, but let's just check the last one. Bromine can be reduced by potassium iodide. Bromine by iodide, that will work, yes, but not by potassium chloride. That also, potassium chloride solution. Bromide cannot be by potassium chloride solution. That is also correct. What am I not getting right here? Oh, yes, there we go. That's not correct. Okay, because that one, that one here can occur, and so therefore that statement is not correct because they've got a not there. Okay, so it is D, not C. All right, just read it carefully. That's what Mr. Lim needs to do as well. All right, oxidation number. We'll try and do these really quickly. So here you got -2, 0, and -1 because this is a peroxide, so you should recognize that. Okay, so not going to have the same oxidation number. Nope. All right, -1 here, -1 here, and this is a hydride. Okay, so the metal hydride, you should recognize that. So that's also a -1. So they're all -1s. So yes on that one. This is +1 because it's a monatomic ion, +1, monatomic ion, and +1, monatomic ion. How do I know that that lithium is a +1? Because I know the CO3 is 2- and there's 2 of them, plus I know that lithium is in the first group, so therefore it's +1. So that one's also. Then Fe, that's +2, that's +3, and that's 0, so that's not that one, so therefore it's only 2 and 3. Okay, and as you see, lots of people got that right as well, so don't get this wrong. Okay, so oxidation numbers, most of the people could do this one, but overall this question, the 7 marks of it was not done well. So let's have a look. Okay, so we need to work out the oxidation number for the chlorine in the CaOCl2 and the HCl. So first of all, let's do with the Ca bracket OCl2. Now, people would get confused with this because they're not really sure about how this works, considering you've got the calcium and the chlorine in there. So what you've got to recognize is that this is an ionic substance. And ionic substances you can split up into their component ions. Okay, so I know that that's OCl1- because there's a 2 there and then there's a 2+ there. So I know that that will be, that OCl must be a 1- ion. Alright, if that's a 1- ion, then I can take and work out the oxidation number here. I know that that's -2. I know it has to equal -1, so therefore this must be +1. So that's +1 there. Okay, then the hydrochloric acid. Here I've got the HCl. I know that this should equal 0 because it's a neutral molecule. That's going to be +1, so therefore that must be -1. So that must be -1 there. Okay, let's move on. Okay, same question. The chlorine gas is produced. Yeah, yep. Okay, so write the 2 half equations showing how chlorine gas is produced from both substances. Okay, so it requires you to remember that the Cl minus, this chlorine here was -1 and this chlorine here is +1. That will give you a bit of an indication about how to bring those both to 0. Okay, so this one here must be the oxidation equation, right? And this one here must be the reduction equation because it's going down. Okay, so that's how we can start with that one. Let's get going with the oxidation reaction. Okay, so the Cl minus from there turns into Cl2 to there plus 2E minus straight from the data sheet. Okay, but you really need to start with this one here, the idea of what's the reactant, right, and what's the product. Once you have those two, you should be able to follow the steps from half equations. Yeah, actually this one here should be half equations. Half equations. Watch that video if you don't understand. Right, there, and then the reduction. So you only need the Ca. You need the CaOCl2. Why do you need the Ca in there? Because it is a solid, so therefore you're not going to be able to get rid of it in an ionic equation. And that goes to Cl2 plus the Ca2 plus. Okay, so this part here, it's an ion because this part here is an ion as well. Right, so it's aqueous solution of CaCl2, but I just know that the Ca will be a ion there because that's what they do. Right, so I have the Cl2, I have the Ca. I need to balance out this equation, so I got the right number of Cl's, I got the right number of Ca's, so I need to go add some waters. So add 2 waters here. Okay, so I need to add some hydrogens here. And then I need to bring this side down. This side is a total of positive 4, and this side is a positive 2, so therefore I need to add 2 electrons onto this side there. Okay. Alright, so a couple of things. Just recognize chlorine gas is the product in both of the reactions there. Okay, it's because produced from both substances. Move on. Okay, so solution contains silver cyanide. AgCN will use to plate a key with silver. Right, so you should be remembering all of that stuff from electroplating and electrorefining. Okay, so just make sure that you do this carefully. So let's have a think. Okay, when you do this thing here, we should remember that whatever you're electroplating is the cathode, because we want reduction to occur here, right? And that must mean that that is the anode. Okay, look here, not always clear in their labeling, and so that probably wouldn't be very good. So let's do that again. This here is the cathode. Okay, this here is the anode. Use arrows to show that and make it nice and clear. Right, the direction of electron flow. The anode is where oxidation occurs, and so it loses electrons, and so therefore the electrons are going that way. Okay, so you can show the direction of the electron flow. The direction of ion flow. Okay, so let's have a think. Ions, we recognize that as the electrons enter the key, it gets more negative, so therefore it has to balance out and have positive things going that way. So the positive ions go that way, and the negative ions go that way. Okay. Also, you should remember that the positive ions are the metal ions that coat the key and electroplate it, so that's why the positive ions go that way. And then the polarity of each electrode, which I hate to do, right? So just remember, you have to memorize that this is an electrolytic cell, and therefore that the cathode is the negative end. Actually, I should probably put that on the electrode. Okay, so electrode, negative electrode, and this is the positive electrode. Okay, you just have to memorize that. All the other logic things there will screw you up when you think of galvanic cells, so don't do that, just memorize it. Okay, so just make sure that you're clear in your labeling. Use arrows to make sure that you're showing what you're doing. Okay, because I'm sure that there would have been some people who just wrote anode here. And if you just write anode here, are you talking about the solution, this area here, or are you talking about this thing here, or are you talking about the beaker? All right, you've got to be really clear, use arrows and show what you're pointing to. Okay. Salt bridge is required in galvanic cells, but not required in an electroplating cell above. Explain the difference between the two cells. All right, so this one, you have to refer to the electroplating cell above. Right, what is said here is that too many candidates listed the differences rather than explaining the difference, and they didn't use this as an example. All right, so in general, you need to talk about the purpose of a salt bridge, which is to maintain electrical neutrality. Okay, once you've done that, how does it do so? It's done by the movement of the ions. And then, why doesn't your electrolytic cell need it? Okay, so you are going to have all of the ions mixed together. And why can you have all the ions mixed together? Because it's not a spontaneous reaction. That's why you have to separate galvanic cells, right? Because if you mix them all together, there'd be a spontaneous reaction. But in an electrolytic cell, it's not a spontaneous reaction, which means you don't have to separate them, which means that you can have all the ions mixed together, and that will maintain your electrical neutrality that will maintain the electrical neutrality for your electrolytic cell. Movement of ions can occur. to maintain neutrality. Okay, that's the idea. And then finally, this is just about something. Final purification step was to remove the iron from the leach solution. To do this, chemists added a suitable oxidant, some hydrogen peroxide, to convert all of the iron 2 to iron 3. Then the chemist added excess sodium hydroxide to precipitate all the iron out. Okay, write a balanced overall equation to show the conversion of Fe2 to Fe3 by hydrogen peroxide. Okay, so again, not clear reasoning, so let's go work through this very clearly. Okay, Fe2 goes to Fe3, and we're going to add in an extra electron there, okay, to balance it out. Okay, this is just writing out the half equation so that we can get to the full equation, but I don't think you actually had to write the half equations out. I'm just going to do it just to show you what to do, right? And then the hydrogen peroxide. Now, if you remember, hydrogen peroxide can undergo oxidation or reduction. Since the iron is oxidizing, the H2O2 must undergo reduction. Okay, that reduction means that it turns into water. Okay, because remember, the oxidation is when the H2O2 turns into oxygen, where it goes from -1 here to 0, right? But here it goes from -1 to -2. So that's the reduction of that oxygen. Okay, so you just kind of need to remember that stuff about hydrogen peroxide. So that forms water. To balance this out, you need 2 of those. Then you need some hydrogen ions here. Then you need some electrons here. Right. Then you can combine it. Okay, so that will make it. You need to multiply this one by 2. And I'm not writing it very clearly considering I wrote this all over the box, but you could probably do it in the margin or something, and then you can write it out. 2Fe2 plus 2H plus H2O2 goes to 2Fe3 plus 2H2O. Okay, what's missing? Probably states AQ, 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 because it's a hydrogen peroxide solution, and that's liquid. Hydrogen peroxide solution. Right, 1 mole per liter. Okay, so that's it. That's all of the redox questions that were there in the WACE 2019 exam, and that's all the videos for redox. Okay, so if you have any questions, you have to go ask me or someone else. Right, just make sure that you try and get through all of these in preparation for the test and the exams coming up. That's it.